really hard for me, but I thought maybe I'll come up with some cool laws in words. But in quant, just as in physics, we don't have any laws, we just have models. And there's a trade-off between conceptual complexity and computational complexity of models. Often physicists create models which are conceptually complex but computationally simple, whereas data scientists tend to create models which are computationally complex but conceptually simpler. And most quant models I know lie somewhere in the spectrum between the two. And well, which ones perform better if you ask? Well, if you ask 20th century physicists, they would definitely prefer the conceptual approach because that's what succeeded there. For instance, when we observed deviations in the orbit of Mercury, there were two options. Okay, one was to add more and more terms in by hand to Newtonian gravity to explain it, and the other was to use this abstract conceptual machinery of Riemannian geometry to explain it, which Einstein did, and he was right. Similarly, quantum mechanics relies on this abstract machinery of Hermitian operators and Hilbert spaces, but computationally it's really simple. You can do it with pen and paper. Well, contrast that to the AI approach, which has become really popular today, where actually you focus on conceptually simple but computationally complex models like neural networks, where compute power or GPU is everything. I mean, look at NVIDIA's stock price, that's a testament to this. And an interesting thought experiment is, would we have general relativity and quantum mechanics if physicists in the 20th century had PyTorch and TensorFlow and lots of GPUs, or we just have neural networks fitting all of reality? Well, let's assume we want to take a step back and try to create those old-fashioned models that those physicists used to create. Well, what principles did they follow? Concretely, these three principles: parsimony, use the fewest possible free parameters to describe a system; falsifiability, your model should be able to be falsified by the data, not just tweaked to fit any kind of data; and it should predict something that was not an input into the model in the first place. And if you look at the most successful models, they satisfy these principles, more or less. So general relativity has just two free parameters: speed of light and gravitational constant. It's very falsifiable. The CMB observations and telescopes have ruled out many extensions of it, and it predicted gravitational waves and black holes before they were actually seen in the data. Think about the standard model. Well, it's a little bit less parsimonious, 19 free parameters, which physicists are trying to reduce, kind of unified theories, but it's reasonably falsifiable. I mean, we falsified a lot of extensions by the LHC, and we predicted the top quark and the Higgs boson before they were actually discovered in the data. Well, what about quant models? Let's look at crash prediction as an example. AI models for crash prediction are millions of free parameters that you have. You can actually tweak a neural network to predict a crash every single day, and I've done this. If you feed it pure noise, you can also predict a crash every single day. And holdout step performances. Anybody who's done a backtest with neural networks, I've never seen a backtest with neural networks that didn't look like this, okay, with flat out sample performance. Well, let's look at SORNet's LPPL model. Okay, so this is a model that tries to see these patterns before crashes. 6 free parameters, so that's a little bit better than a millions. It's partly falsifiable, but even if you give it pure noise, it can predict a crash like every few days. Not every day, like neural networks, a little bit better. And out of sample that was proposed in 2001, you can check if it predicted crashes after that or not. The jury's out of that. Let's look at an even more parsimonious model. It's a dynamical systems model of crash. Just one parameter, which comes from an SD. It's falsifiable, doesn't spike when you give it pure noise. And it actually describes something you didn't feed into the model in the first place, which is increased cross correlation of stock returns before the crash. So all the kinds of models we've looked at fall somewhere in this whole spectrum. And what I argue is that most quant models are too much towards the right side, and we need more and more modeling towards the left side of this equation. And think about some of the problems that most quants complain about. There's too little data we have, our models are overfitting, they are unable to handle regime shifts, and I think a lot of these can be handled by creating models more and more towards the left side, which are conceptually complex, computationally simple, and more parsimonious. So I didn't come up with any laws, but I have 3 commandments that we follow very religiously at our firm FMI that are there for you to see. So, create parsimonious models, create falsifiable models, and don't trust any model that was not tested on something that wasn't fed into it in the first place. Thank you so much.